All right, so 7.2. We're going to take what we learned back in basically almost every chapter so far, and we're going to do the same thing to the graphs of exponential functions. So remember, you've got your four parameters. Now remember, we're going to start with the base graph in this case of y equals c to the x, and then we're going to transform that. So notice where the parameters are. A is in front of the function. And remember that A causes a vertical stretch by a factor of A about the x-axis and a reflection over the x-axis. B, remember, is in front of the x, and because the x is as the exponent, the B will also be part of that exponent. You can see up here at the top where B is. It's in the exponent along with the x minus h. But remember that B causes a horizontal stretch. That stretch factor is about the y-axis, and it's by a factor of 1 over b. Whatever happens to the x happens to the bx and the x minus h. Again, the x minus h is in the exponent because that's where the x is. And the value of h is the opposite of what it appears to be. It shifts the graph left and right because the general equation has x minus h in it. And then the value of k is after the b bracket x minus h. It's separate from it. That's why it's not an exponent, and that shifts the graph up and down. Okay, so same principles that we used before when we dealt with transformations. So in this case here, we want to do a transformation of y equals 3 to the power x. And we want to transform it to 2 bracket 3 to the power x minus 4. So we've got here a partial table, a table of values for y equals 3 to the x because that's our base graph. Right? When we look at this equation here for part A, this is a transformation of y equals 3 to the x because the base is still 3 and you still have an x as the exponent. But there's something extra there. So we need to determine what that something is and what it does to the graph. But we'll start with the number in front because remember the order that we do our transformations can be important. You always do your stretching and reflecting first, your translations last. And so we have to do it in the order that they appear as long as you have y by itself first. Because that'll be the a parameter, then the b parameter, that's your stretching and reflecting. H and k cause the shifting. So we've got an a value of 2. Now, if we wanted to write this equation with an a value of 2 there, we would say y equals 2 times 3 to the power x. That shows an a value of positive 2. Right? And what it does when a equals 2, and we'll write it maybe down below here, remember that will cause a vertical stretch, and you have to state about what axes. It's about the x-axis because it's a vertical stretch, and you also have to state the scale factor. It'll be by a factor of 2. And so we remember that when you vertically stretch by a factor of 2, it's the y values that get multiplied. They get multiplied by the stretch factor. So for our table of values, we're going to multiply all the y values by 2. So 1/3 times 2 will become 2/3. 1 times 2. 3 times 2. 9 times 2. And 27 times 2. Vertical stretch by a factor of 2. Verticals up and down. It's the y values that go up and down. Right? Then we have the fact that x is replaced with x minus 4. Remember that it's the h value that's hooked together to the x with a plus or a minus, and the value of h is the opposite of what it appears to be. So this will be an h value of positive 4. This will shift the graph 4 units to the right. So now if we add this into the equation, If you shift it 4 to the right, that means you're going to add 4 onto all the x values. The y values won't change this time around, but we're going to add 4 onto all of the x values. Add 4 onto all of the x values. Because we have an h value of 4, so that will shift the graph 4 units to the right. So if we put these points on the graph, we've got the point 3 comma 2/3, really close to the x-axis. We've got the point 4 comma 2, a little bit higher, 5 comma 6, and 7 comma 54. So 54 will be about right there. Remember that these exponential functions have an asymptote. The base graph will always have an asymptote, which is the x-axis. The only thing that would change that is if the graph was shifted up or down, because the x-axis is a line y equals 0, so even if you vertically stretch that, it's not going to change. Points on the x-axis would be invariant. So the x-axis is still an asymptote. And the graph will look something like that, with arrows on both ends. So if we want to talk about the characteristics, the domain actually won't change. It'll still go from negative infinity to positive infinity. Neither will the range change. It'll go from 0 up to positive infinity. And again, the 0 is not included because the x-axis is an asymptote. It'll get infinitely close to that, but never touch it. We have a horizontal asymptote as an equation. Remember that an equation must have an equal sign and a variable. It is the line y equals 0, the x-axis. There is no x-intercept. Because the x-axis is our asymptote. But there is a y-intercept, and we can calculate it. Remember, the y-intercept is always where x equals 0. So if we take the equation and we set x equal to 0, it'll be 2 times 3 to the power 0 minus 4. Or 2 times 3 to the power negative 4. That power negative 4 applies to the 3 only, so when you move it to the bottom, only the 3 moves. And that'll change the exponent sign to positive 4. And 3 to the 4th is 81. So there is the y-intercept. If we want to write it as a coordinate, it'll be 0, comma 2 over 81. Y-intercept is always where x is 0. Let x equal 0 to calculate the y-intercept. Okay? So again, we want to start with our base function y equals 3 to the x, and now we're going to transform it to y equals negative 1/2 3 to the power 1/5 x, take away 5. So again, we'll start with our a and b values. Always do our stretching and reflecting first. The first thing we see here is that we have an a value of negative 1/2, and you have to remember that causes two different transformations. You're going to have a vertical stretch as well as a reflection. So it'll be a vertical stretch, and remember you always have to state about which axes. So vertical stretch about the x-axis, as well the scale factor. That's by a factor of 1/2, and then the negative part is your reflection. It's a reflection about the x-axis. When either a or b is negative, there's actually two transformations there. But we can do them simultaneously by multiplying all the y values by negative 1/2. That'll do them both. So when we write our points for y equals negative 1/2 times 3 to the x, all the y values will be multiplied by negative 1/2. So in this case, the x values won't change. The y values are multiplied by negative 1/2. Then we have a b value. Remember, b is in front of the x. Whatever happens to the x also happens to the bx. In this case, they're both as an exponent. A b value of 1/5. And we remember that when you have a b value, that's a horizontal stretch. And again, you have to say about which axes. In this case, it would be about the y-axis. And you also have to remember that the stretch factor is the reciprocal of b. This would be a horizontal stretch by a factor of 5, the reciprocal of 1/5. Which means now all the x values will be multiplied by 5. So that's our next step. For y equals negative 1/2 3 to the power 1/5 x. As we said, that's a horizontal stretch by a factor of 5. All the x values will be multiplied by 5. Right? So there's those points after we've done that. And then finally, we've got that minus 5 on the very end. That would be a k value of negative 5, which means the graph is going to shift 5 down. which means you're going to decrease all the y values by 5. So this last step will be our final step. By subtracting 5 from all the y values. Now, negative 1, 6, take away 5. So that would be negative 30 over 6, or 30 over 6, that's 5. So negative 1 take away 30 would be negative 31 over 6. And you could certainly write it just as a mixed number, negative 5 and 1, 6, but it's still going to be negative 31 over 6. Negative a half take away 5 would be take away 10 halves. So negative 1 half take away 10 halves would be negative 11 halves. Negative 3 halves take away 10 halves would be negative 13 halves. Negative 9 halves take away 10 halves would be negative 19 halves. And negative 27 halves take away 10 halves would be negative 37 halves.
Before you said that nothing could, you would be able to have any x-intercepts.
But this graph is shifting down 5 units, so the horizontal asymptote is also going to shift down 5, right? And I know as soon as I said that, you knew exactly. Yep. That's okay. See, Jonathan, I told you she was smart. You told me no, but yes, she's smart. You're going to have a 2-hour conversation tonight now. You know that, right? So good luck with that. Okay, so there's our horizontal asymptote. So our points, negative 5, comma, negative 5 and 1, 6. So that's just below negative 5, just below the asymptote. And our next point is 0, comma, negative 11 halves, or negative 5.5. It's a little bit lower than the previous point. Then 5, comma, negative 6.5. Approximately there. 10, comma, negative 19 halves would be negative 9.5. So just slightly above negative 10. And 15, comma, negative 37 halves, which is negative 18.5. Close to negative 20. Because this graph was reflected over the x-axis, it goes downwards instead of upwards. So there's our sketch. So our domain has not changed. It'll still go from negative infinity to positive infinity. But the range will. And when you write an infinite notation, it's always smaller value to larger. So you must go from negative infinity up to negative 5. And again, those are not included because the negative 5 is where our horizontal asymptote is. So there's our domain and range. Again, we just mentioned our horizontal asymptote. It's an equation, which means you need a variable and an equal sign. It'll be on the line y equals negative 5. Because every point on that line has a y value of -5. Again, this graph has no x-intercept. But we can see that there is a y-intercept. And in fact, in our table, we actually found the y-intercept. The point 0, -11 halves. The y-intercept is always where x equals 0. So we have this point on our table. We don't have to algebraically determine it. So our y-intercept is at 0, -11 halves. Okay, but if we didn't know from our table, we would let x equals 0 in the equation to get it. Okay? Now on this next one, the only difference is that it's a different base graph. So you'd have to determine or generate your initial table of values from the graph of y equals 4 to the x. So in this case, our base graph or our base function would be y equals 4 to the power x. And it tells us that, right? Transform the graph of y equals 4 to the x. So again, the only difference here is you would need to generate your initial points. And you do this just by using a table of values. And you can start with values of x from -2 to +2 or whatever you want. You know, you probably want 5 or so points. And then go through all of the transformations. Okay, so not going to do this one. It's really the same principles that we did on the previous one. So let's just continue on. So on the next page, we've got an example here where we want to model a situation. A cup of water is heated to 100 degrees Celsius and then allowed to cool in a room with an air temperature of 20 degrees Celsius. So when you put it in the room, the temperature is always going to decrease. The temperature T in degrees Celsius is measured every minute as a function of time m in minutes, and these points are plotted on the coordinate grid. It is found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. A smooth curve is drawn through the points, resulting in the graph shown. And you can see that you have your axes labeled along the bottom, the time in minutes. Along the side is the temperature in degrees Celsius. Note that the horizontal asymptote is at 20 degrees because that is the temperature inside the room. So when you look at this, it's kind of telling us that the temperature will never actually get to 20 degrees. And the reason for that is it says that the water decreases exponentially at a rate of 25% every 5 minutes, which means it's maintaining 75% of its temperature every 5 minutes. Losing 25% means you're maintaining 75%. So if you want to find your temperature every 5 minutes, you take 75% of the temperature of the previous 5 minutes. And when you take 75% of something, you're always going to get something. It'll never get to be 20. And we're going to see that when we get our equation here as well. And so that's what it asks us to do. What is the transformed exponential function in that form? Y equals a times c to the power b bracket x minus h plus k that can be used to represent this function. So maybe the easiest place to start is with our k value. Our k value would have to be plus 20. Normally, these exponential functions have the x-axis as the horizontal asymptote. This one has the horizontal asymptote at y equals 20, or t equals 20. So the graph has been shifted up 20 units. So our k value is 20. And you're going to see that in the case of these exponential functions, like we saw in the previous one we did, the K value tells you where that horizontal asymptote is. And the horizontal asymptote tells you what the K value is. So K equals 20 because this is where our horizontal asymptote is. And you might also remember in the last class we talked about what our A and our B values tell us. A is normally the initial amount, but that is only true if the graph hasn't been shifted up and down or stretched vertically. We already know this one has been shifted up, so A in this case will not be the initial amount. It won't be 100, which is our initial temperature, but B is always the growth factor, and in this case it is the decay factor. And to determine that, again, you got to go back to what percent is it maintaining. It's losing 25%, so that means it maintains 75%. That will be our B value. B will equal 0.75 because that is our growth factor. And in this case, it's more accurate to say it's a decay because that's what's happening. Right? The temperature is decreasing, but it doesn't really matter how you describe it. It basically tells you how things are changing. Now, because in this case, and we're going to see that when we deal with these growth and decay formulas, it always follows this format. So I'm just going to write this at the top. It's y equals a times b to the power t over p. And this is on the formula sheet. A times b to the power t over p. It's on the 30-1 formula sheet. So if you have yours, you can get it out and see it. It's there. Right? And so remember that B will always be the growth factor. T will be the time. So let's write this out. B will be the growth factor. T will be the time. And P is the growth period. How long it takes for the growth or decay to happen. And in this case here, because we're using the 0.75, and that comes from the fact that the temperature decreases exponentially at a rate of 25% every 5 minutes, that's what P will be. That's the growth period. That's how long it takes, in this case, for the temperature to decrease by 25% or maintain 75% of its original temperature or the temperature of the previous 5 minutes. So that is what P will be. P will be 5 minutes. That is the growth period. So originally, we're going to write this in the format of what's above, except we're going to have that K value on the end. Okay, so I can start to write this equation now. I can say y equals, I don't know what A is, but I found the base, whether you say it's C or B, the base is 0.75. And the exponent will be T over 5. Right? The general form is T over P, but we've now determined that P is 5. P is the growth period. And we've got that plus 20 on the end. So all we're missing here is figuring out what A is, that initial amount. And again, it's not really the initial amount in this scenario. If there is no shifting up and down, there is no vertical stretching, then A is the initial amount. But in this case, the graph is shifted up 20 units. So we can algebraically determine what A must be because we do have the temperature at time 0. At time 0, the temperature is 100. So we can let y equal 100 and t equals 0. And now we can determine what A is. And we've used this technique before in this course. Right? If a graph goes through a point, that point must satisfy the equation. So we can subtract the 20 from both sides. That'll give us 80 on the left. Also on the right, you're going to have A times 0.75 to the power 0, because 0 over 5 is 0, and anything to the power 0 is 1, which means A equals 80. And now we can write this equation. The equation will be t the time will equal 80 times 0.75 to the power m over 5, if we want, where m counts for the number of minutes, plus 20. So the capital T is the temperature of the water, the little m is the time in minutes. So there's our equation. Okay? So this next example is talking about a radioactive element that's used in household smoke detectors, and its half-life is approximately 432 years. So that means that it takes 432 years for whatever amount is in that smoke detector to begin with to decay to half of what it originally was. Once we get the word half-life in there, that also tells us that the base is 1/2. Okay? Notice that the equation, or the graph I should say, has the x or the t-axis as the vertical asymptote. So this graph has not been shifted up or down. So A, the amount that's left, okay, can be found by, again, using this formula, A times B to the power T over P. And in this case, little a will be the original amount. It will be 200 grams. Because this graph has not been shifted up or down, the horizontal asymptote is the x-axis or the t-axis. A would refer to the initial amount, and B refers to the growth factor, which will be 1/2, because the amount of this radioactive element is being cut in half. And because the half-life is 432 years, that is our p-value. That's our growth time or growth period. So there's our equation. A, the amount, can be found by using this equation. Now, we could have done this on the last one, but we'll do it in this one instead. You can use your calculator. You can put this equation in there, or you can just use the equation. When I say put the equation in there, I meant you can graph it to make sure the graph looks like this one here. Or you could use the equation and choose a few values of t from the graph. And you can tell from the graph what A, the amount, should be fairly close to. So you can check a couple points to make sure that your equation looks to fit the graph. So what do I mean by that? Well, if t is 900 years, so you can see that the value of A, the amount, should be between 40 and 50. Maybe a little closer to 40 than 50, maybe, but between 40 and 50 nonetheless. So 200 times 0.5 to the power 900 over 432. I'm letting t the time equal 900 years, and there we go. we get an answer of 47, which is between 40 and 50. Okay? Let's check another point. 1800 years should be just below 20. So let's check that one. So this is 1800 years. And that number is below 20. Okay? The one point that we know for sure is on this graph is the point 0, 200. And that'll work when t is 0, 0 over 432 is 0, 1 half to the power 0 does equal 1 times 200. So that point definitely does work. The other ones, it's kind of a guesstimate that your equation seems to work for the points, and this one does. Okay. So that's transformations of exponential functions. I've got some questions for you to work on. I will post the solutions to Google Classroom so you can check your answers. I would encourage you to definitely do that. Okay.